Hello everyone. So previously we learned about Taylor expansion of a single variable. In this video we learn about the Taylor expansion of multivariable functions. So, the Taylor expansion for a single variable was something, let's take a better marker, was something like this: x minus a f prime of a plus x minus a squared over 2 factorial f double prime of a, and so on. This was the single variable case. Now, what shall we do for a function of two variables? So, how to Taylor expand this? So how do we do this? So for ease, let's consider we will Taylor expand around x equals 0, which is basically the Maclaurin series, or the Maclaurin expansion. So what will this be? So let's consider a two variable function, f of x and y, and it starts from 0 to infinity, m equals 0, infinity. C and m, these are the coefficients, and xm, ym, because Taylor expansion is basically expanding in powers of the variables. So if we write it out, the first one is this coefficient 1, 0, x, because if this is 1, 1, if it's 0, the whole thing is 1, plus c 0, 1, which is, now we have the y thing, we have c 2, 0, which is x squared, c1, 1, which is xy, c0, 2, which is y squared, and so on. Now the first question is, how do we get these terms? First, if this is 1, this is 1. If this is 0, 0. So we just have x, 0, 1, 0, 1. We just have y, 2, second power, 0, none. So 1, 1 is one of each of these, and so on. This is how we captured the coefficients and the expansion and the series expansion. Now the big question, how do we find out these coefficients? We use a similar technique. What did we do in the case of a single variable? We took derivatives to find out the coefficients, right? So, but there is an issue. The issue is we have a two variable function, right? But our Taylor expansion previously was for a single variable. It's simple, since we are dealing with two variables, we have to consider partial derivatives to find the coefficients. So the coefficients would be, would be c0, 0 would just be f at 0 and 0. c1, 0 would be the first derivative with respect to x, the partial with respect to x, and this would be partial with respect to y, and c1, 1 would be partial with respect to x and partial with respect to y. Similarly, C20 would just be x squared. Okay, so C20 would be the partial with respect to x squared, or the second partial derivative. I missed. Yeah. So let's write the coefficients. See, n0 would be, with a similar analogy to this, it would just be 1 over n factorial similarly yeah, this is how you would find the coefficients. So the coefficients can be found out by partial derivatives. So let's write the Maclaurin series expansion of this function. Okay, let's erase this part. So the Maclaurin series expansion of the function of two variables can be written like this, or the Taylor expansion around x equals 0, 0 to infinity, 1 over n factorial, x plus y right, and the function. If we want to make this a Taylor expansion, we just replace x minus, we have to put an expansion with respect to a point, let's say with respect Taylor expanding around a and b, the point a and b, a comma b. This would just be n factorial x minus a. Oh, I ran out of space. Let's just write it here. So Taylor expansion around the point a comma b, this would be n equals 0 to infinity 1 over n factorial x plus y minus b delta y n xy. So what did we do here? First, we found out the coefficients can be found out by partial derivatives. So how did we do that? It's with analogy to the single variable. If you want a rigorous proof, you can ask me and I will provide you a rigorous proof of how we can get the partial derivatives. The coefficients will be equal to the partial derivatives. You just ask me on Slack, I will just give you a proof. But for now, you can, if you want a direct analogy, you can extend from single variable to the second variable case. So this is now the Taylor expansion around the point a comma b. This was, the point here should be 0 comma 0 because we have a two variable. This should be a two variable thing. And yes, this is the Taylor expansion.